That's going to be kind of hard for us to do, to write that scatter plot down. So let's just watch me work through this, graphing those two lines. So the first one, g of x equals 13x plus 25. I'm going to graph that one in red. Okay, so if I look here, 13x plus 25. All right, so 25 would be my y-intercept. That would happen right there because we're going up by 25s. Right, this is 25, 50, 75, 100. So right here at 25, this would be my first point. And then the slope was 13. So we could treat that as 13 over 1. Or we could really write that as 26 over 2. And so the reason that I would say, well, let's see if I like that. If I like something different. 26. Okay, so I don't really like either one of those. So the slope is 13 over 1, but look how much my y's are going up by. So we go from 0 to 2.5 to 5, 7.5, 10, 12.5, 15. So my x's down here are going by 2.5s, but really 5s is the best number to look at there. So 13 over 1, what if I multiplied the top and bottom by 5? Well, then that would give me 65 over 5. 13 times 5 is 65. 1 times 5 is 5. So this may be new. You may not have seen this before. But 13 over 1 can be rewritten to be 65 over 5. Like if I divide these, I get 13, which is what my slope is supposed to be. So instead of the slope being up 13, right 1, I'm going to go up 65, and I'm going to go right 5. It's just going to be easier because I'm going to stay right here in line with these 5s. I don't have to guess where's 1, 2, this is 2.5, 3, 4. It'd just be a lot uglier if I kept going by 1s. Up 13, right 1. So if I go up 65, so that's up 25, up 50. So up 65 is going to be somewhere in here. And then if I go right 5, that's going to put me somewhere in this ballpark because that's the next value of 5. So my next line, or my next point, is going to be somewhere in here. So let's zoom in here. Okay, let's do it again. And if I go up 65 and right 5, so I went up 15, so I got to go up 35, and then this would be 25, that's 60, so 65 would be about right here. And then right 5 would put me here at 10. So here's the next point. And so I've got 3 points. That's probably enough here to kind of graph that line of best fit. So do you think that's a pretty good line of best fit? It kind of is pretty reliable with the data. Okay, let's look at this other one. Let's look at 12x plus 30 and see what it would look like. So here my y-intercept, instead of being 25, is going to be 30. So it would be plotted right here. And now then the slope is 12 over 1. So again, I'm going to go by 5s. So that is going to be 60 over 5 if I go that way. So are these slopes kind of close? Or the y-intercept's kind of close? Yeah. So let's see what happens when I graph this one. So if I go up 60, so I am at 30. So I need to go up 60. That will put me at 90. So that'd be right here. And then right 5, that's going to put me somewhere in this ballpark. And then if I go up 60, that puts me at 150. Right 5 puts me somewhere in this ballpark. And so then the blue line would be somewhere in this ballpark. So would you say that that line is a good line of best fit? It kind of well represents the data as well. Yeah, they both are pretty valid. So it says, what is a reasonable domain for each function. So this is what they're talking about, reasonable domain. So what's the question about? The question is about temperature at the beach, right? And the domain, does anybody know what domain means? Yeah. The domain is all possible x values. All possible x values. So right here, when I look at my x values, what are we talking about? How many degrees above 80 degrees it is. Okay, so if you think about domain, if it's below 80 degrees, there's probably not going to be very many people wanting to go swim at the beach, right? And we are talking about July here as well. So how high could these x's go that make sense? So if this is 5, that means we are 5 degrees above 80. So this would be 85 degrees. This would be 90 degrees. 100 degrees. All right. Could it be a little bit hotter than 100? Probably. I would say 30 up to 110. It's probably not going to get much higher than 110. Right? It definitely doesn't make any sense to be talking about 100 on the x's. It's not going to be 180 degrees. Right? You're not going to go that far to the extreme. So what's a reasonable domain for the function? Well, let's just say from 0 to 30 would be reasonable. And then explain why. So I'm not going to do that in words. I just explained to you why. Because we're talking about how many degrees above 80 degrees it is. It would make sense to be talking about 150 degrees. And then C. Which of these models is a better predictor of the number of beachgoers based on the temperature above 80 degrees? And defend your model. So between the red line and the blue line, which one do you think is a better predictor of what they need? Why?
Because it don't go. I mean, it kind of. I don't know, honestly.
I'm with you. It's not really easy to tell which one's a better predictor, right? So the red one, this is what I'll tell you. The red one kind of stays right here on the bottom.
Yeah, wait, is there a dot like on 20 at the top up there? I can't really see it. All the way at the top.
Yeah, there's a dot here.
No, it's not like with the red line.
No.
Okay, then, yeah, because it only goes up to 90 degrees. Right? You said 5 would be 85 and 2 would be 95. I mean, 90.
Yeah, this would be 90 degrees. So
Okay.
this would be 95 degrees. This was it being 97 degrees here. That's what that dot's for. So when it was 97 degrees, the number of people at the beach was about 250. Right? It was a lot higher. But when it was 85 degrees, there was only about 50 people at the beach. So the hotter it is, the more people go to the beach. Both of these predict that. But the red one kind of stays towards the bottom of the data, where the blue one trends more towards the top, but then it kind of flattens out when they meet later on. So the moral of the story is, which one's a better predictor? Hard to say. They're both pretty good. Like, there's neither one that's just way off. Like, you don't have a line that's just going crazy bad. Well, what we're going to do today is we're going to be able to measure which one is better using those graphing calculators. Point 768. 7768?
Yes.
Okay, that's good enough. All right. Did anybody get a different A?
No.
Okay.
Would you not round the second 7 to 8?
You can. If you want to write it as 0.78, that's fine. That's fine. I just rounded to 4 this time. It doesn't really matter what I round to. Okay, we're not getting that real picky about it. That's not the purpose of this. Okay, so our A is here. And what do we find the B to be?
4.69062.
Okay. 4.6902. 5, so 03.
Yeah.
Yeah, sounds good to me. So it's 4.7. So now,
And then for A, would you stick with 0.7?
no, it would need to be 0.8, right? Because the 8 tells the 7 to go up. So your equation of the line would be y equals 0.78x plus 4.7. That's what my line would look like.
This won't be easy. It's going to.
Yes.
Where did you get 4.7?
Okay, so you have it at 4.6.
In your, yeah, what was it? Y'all got 4.6.
Yeah, and if you round it, you get
What was it supposed to be? 4.6.
4.69.
Okay, so 4.69. And so the 9 tells the 6 to round up. So I rounded up to 4.7. Okay? Any questions here?
There is no plural. Yeah, that's one of the words.
Okay. Let's go to the next example. So right here is our example 2. It says, what does the correlation coefficient reveal about the quantities in a bivariate data set? All bivariate means is we have two variables. So we have an x and a y. So when you perform a linear regression using technology, you're also given a correlation coefficient. The correlation coefficient is represented by R, and it's a number between -1 and 1 that indicates the direction and strength of the linear relationship between two quantitative variables in a bivariate data set, a set of data that uses two variables. So when you plug in all those points, like we did yesterday, and it shows us our A value and our B value for our line, there's also a way you can turn on your calculator how to see these two values. So you have an R squared and an R. This R is called the correlation coefficient. So you can see here our number was 0.995. So let's talk about what this number means. It tells us it's between 1 and -1. Okay, so first thing that the number tells us is the direction of our line. So if the correlation coefficient is a positive number, then that means our line of best fit has a positive slope. So when you look here, this line is going up, right? Has a positive slope. So anytime our number is between 0 and 1, we know that it has a positive slope. If our number is negative, like so here, negative 0.284, then that tells me our line of best fit has a negative slope. So again, a positive correlation coefficient means the line has a positive slope. A negative correlation coefficient means it has a negative slope. Any question about that part? Now, the second thing that the number can tell us is how close to a line is our points. So again, these scatter plots are just a collection of points. So like for instance right here, it's all these red dots are a collection of points. The closer to a line that these dots are, the closer to 1 our value is going to be. So again, because this is 0.98, that's very close to 1, which means these dots look very much like a line on their own, without a line. You look at the example beneath it, This is negative. The negative again tells me there's a negative slope. But the 0.28, that number is closer to 0 than it is to 1. Right? So the closer to 0 the number is, that means our points are more sporadic. They do not look very closely like a line. So you see here how the points are spread out? That's not much like a line. All right? When you look down here at this last one, I've kind of cut it off. But look at this number. It's negative 0.995. So the negative tells me my line of best fit has a negative slope, which this one does. And then 0.99 means these points are very close to making a line on their own. And you can see here at the very beginning, these 3 points are right there on that line. So you can just imagine as we continue down this line, the points are going to continue to be in a linear fashion. Okay, so the slope of line is positive. And then what else does it tell me? Is the data going to be close to a line, or is it going to be very spread out? Okay, so how do we tell? How do we know if it's close to a line or very spread out and sporadic? The number. What makes it close to a line? If it's close to 1. What makes it sporadic? If it's close to 0. Or what is this number? 0.1. So is that closer to 0 or 1? Closer to 0. So we would think that the data is going to be very sporadic, very spread out. So it's a data not close to a line. So what we can imagine this looks like, if I have, here's the line of best fit that they gave me. The data is just going to be all over the place. That if I took that line away, like I really don't even know if that data even be close to that line. Right? That's what I expect the data to look like, something like that. Because that number is closer to 0 than it is 1. Okay, when you look at B part, what does the negative tell me? The slope of the line is negative. So we could say the slope of the line is negative. And then 0.6, what does that tell me about? Are my points close to a line or not close to a line? Yeah, it's somewhere like right in the middle, right? I mean, 0.6 is almost 0.5. So the data kind of, so let's just say sorta. That's a terrible math word, but I'm going to do it. Sorta looks like a line. So what I'm imagining there is if I had, again, a negative sloping line, and I were to look at the data is not going to look like this, right? That would be closer to like 0.9 or 1. But it's going to generally trend downward. Right? So when I look at this, if I took that line away, I can clearly see there's a trend. Now it's not a lot like a line, but the trend is still very evident that from left to right the data is going down. I would expect something like that. Okay. This says a student found a positive correlation between the number of hours of sleep his classmates got before a test and their scores on the test. can he conclude that he's going to do really well on the test if he goes to bed super early? What do you guys think? Okay, so just because there is a correlation, you can't say that one causes the other. So going to bed early doesn't necessarily mean you're going to score well on the test. Those students that went to bed early and got more sleep may have done so because they felt confident in the material. They didn't need to spend time studying, right? So causation describes a cause and effect relationship. A change in one variable causes a change in the other. But to determine whether two variables have a causal relationship, you have to carry out an experiment that can control for other variables that might influence the relationship between the two target variables. The student cannot conclude that he will do well if he goes to bed early. Other variables like the time spent studying or proficiency with the content could affect how well he does on the test. So if you saw this and said, if I go to bed early, I'm going to do well on the test, then people would just sleep in class. They go to bed even earlier. Well, if you sleep 20 hours a day and you sleep through math class, I promise you're not going to do well on the test. Okay? So this is all about causation and correlation. Just because something is related, you can't say that one causes the other. That they just go together in some way. So like a lot of times you see studies about like how well underprivileged kids score on tests, right? So are they scoring poorly because they are struggling, their family struggles financially more so than other families? Or is it because of a language barrier? Or is it because of they're uninterested in school? Or is it because their culture doesn't put an emphasis on school? Right? There's a lot of reasons why it may be true. But we can't say that just because someone is in a socioeconomic struggling class that they're going to do worse in school. That doesn't go hand in hand. There's all these other factors that go into it. So that is what this is talking about. Don't just be so quick to judge one because of the other. So here it says, be careful not to assume if a correlation exists between two variables, a change in one causes a change in the other. The change could be caused entirely by a third unknown variable that we have not spent time studying. So you have to do more research. Okay, let's look at B part. It says a lifeguard notices that as the outside temperature rises, the number of people coming to the beach increases. So can she conclude that the change in temperature results in more people going to the beach? Well, in general, yeah, I would say that's probably true. The higher temperature it is, the more people go to the beach. But she didn't carry out an experiment or a control for other variables that might affect the relationship. So why else do you think more people might go to the beach when it's hotter? It feels better? Okay. Okay. What about more people go to the beach because they don't have school in the summer? So could the increase be due to no school, so more people are there? We don't know for sure, right? There's all these other factors that could play into it. So she can't conclude the only reason more people come is because of the temperature, because she didn't do a full-on experiment to control that.